problem. Right? So it's about the map. If I have x right there, and you bring this one, you can view this as an integer, right? But you can bring this one integer down there into M world and reduce it to mod M. So if you make it even further smaller, right? So I use a different notation, x1. If this is 15, that might be just 2. Things like that. Does that make sense? Where I switch the notation? If you take that large number, bring it down to mod M world, it takes least residue and change it again. That was this map. So when you do the homework last night, did you kind of understand what this map is? Not proving this bijective thing. Did you understand this map? Not really? For example, like this, Z mod 15, right? And Z mod 3 cross Z mod 5. This is the map I'm describing psi. I take 11, where is it going, right? If you put 11 down to mod 3 world, what is that element? What is 11 congruent to? I thought that was a 2. Is that right? 9. How about 11 going to 5? What is that? It's 1, right? 10 is that. So 11 is going down to 2 and 1. What is that map? Just reducing to mod 3 and mod 5. That is the map. That's pretty innocent map, isn't it? Very simple. You know it. That was the definition. So definition makes sense, right? And part of the homework is that you're showing this one is bijective. So going backward is a surjective, right? So let's do surjective. You don't know this M11, right? You don't know 11. What you know is that there's this guy x that I don't know. This is 2 and 1 if you reduce in mod 3. So can I write it like this? If I reduce it in mod 3, it becomes 2. Is that right? If this guy reduced to mod 5, it becomes what? 1. I don't know what that is, but it has this property. How do you figure this one out? X. What theorem do you use? Chinese remainder theorem, right? So how do you know there is x in there? How do you know there is x in there that maps to this 2, 1? How do you answer that question? Short. Chinese remainder theorem guarantees the existence of such x. Correct? So this weird thing is a fancy version of Chinese remainder theorem. Fancy version of Chinese remainder theorem. So surjective got to be injective because you have the same number of elements. You have mn elements, right? M times n, mn elements. How can this be non-injective? That's not a proof, you know that, right? But surjective forces this one to be injective, so that's bijective. Difficult part was that if you choose an invertible element here, star makes sense? And if you choose an invertible element there, Chinese remainder theorem guarantees that there's going to be something here, right? But that's also invertible. That's the part 2 here. So this map behaves awesomely nice. Invertibility and the squares here, then squares there, pull up as a square is wonderful. Every arithmetic breaks down under Chinese remainder theorem. So you don't have to look at this world. You look at always the prime power world and glue them together using Chinese remainder theorem. So fundamental question goes down to how do we do the arithmetic down in there, Z mod P to the n world? Because Chinese remainder theorem allows you to split it through relatively prime. Is this some vague discussion kind of make sense? Yeah. This behavior, this map has a wonderful behavior. All the arithmetic is preserved, not only invertibility. You will see over and over again. So fundamental question go down to, how can we do the arithmetic there? We did that division. Remember the division, long division? That was a prime power version, right? That's why that part is important. You can do that in here. If you can factor, the factorization becomes hard. So we will assume this. You happy about that? We're going to assume this fact, right? We're going to assume this fact. So if this is true, so also try to look at this version here. Psi has domain this size, right? If you want to restrict your map to something else, but kind of preserving the map exactly the same way, you have to introduce a different notation in function. Because function comes with the codomain and domain altogether. If it's different, you use a restriction bar something. So use this slightly different notation, reduction. What is this one? There's a star there. Again, anybody remember the star definition? What does that mean?
Invertible elements.
Invertible elements right there. Invertible elements goes to invertible elements, landed perfectly. And this is bijective as well. We can assume that, right? Not only this is bijective, this is bijective. So I want you to quote that correctly. So let's have a practice. Practice writing psi, like start like that. And write down, okay, here's a function, z mod mn goes to z mod n, z mod cross z mod n. Is bijective. You write that down. And this induces non-trivially, right? It's a non-trivial result. Invertible map to invertible map perfectly. Bijective. What is our fundamental question here? What is that we're trying to answer here?
We want to show that the Euler function is multiplicative.
That's right. We're calculating this, isn't that right? This is what we're calculating. How many elements are there in z mod mn? This is relatively prime to m times n, right? So that means that we're counting this element in here, right? That's exactly what the phi of mn is, right? Bijective allows you to count it here, is it not? Bijective allows you to count it here. What is this guy? How many elements are here? Is that right? Times phi of n. They are bijective map, therefore they're equal to each other. Is that right? Isn't that showing the power of this map idea? As you advance to a higher and higher mathematics, you will see more and more of this map technique to give a clear picture. This is thought as an advanced formulation, so they don't expect some of the beginner level undergraduate students to accept this type of idea. So that's why the book is written out, word using different ideas. But as soon as you accept this functional terminology better, so-called isomorphism. Did you hear about the isomorphism? This is the idea of isomorphism. Turning this complicated object to a better decomposed isomorphism, which is the same thing in mathematics, then you see clearly. You think much more clearly. That you did that in linear algebra too. Decomposing eigenvectors. There's this massive matrices, so complicated, diagonalize it, that's exactly the same idea. A complicated object broken down to a clear, easier to understand, we call the decomposition idea, right? Decomposition. So it's a decomposition. So if you have that picture, it's so easy to count it here, right? Phi of mn equals phi of m times here. So with this theorem under control, do we seem like we have a proof? Phi of mn equals phi of m times phi of n. Therefore, we have that full version with the P1, E1, and P2, E2, that thing. Good?